A night fighter airborne interception radar can hold a contact from about 2 miles, giving range and bearing, but not permission to fire. In the congested airspace over the invasion corridor, a trigger pull has to clear visual identification, not just a return on the scope. On the night of 12 to 13 June 1944, a de Havilland Mosquito from No. 4 10 Squadron of the Royal Canadian Air Force is vectored onto a Heinkel. He, 177A5, believed to be carrying HS-293 radio-guided glide bombs for an anti-shipping strike. The radar operator works the display and feeds corrections. At 2 miles, the return says only, "Large multi-engine, nothing more." The pilot closes into the dark with one rule. Until the target is seen and recognized, the guns stay silent. Recognition must come from the silhouette, not the scope. That limitation defines the fight. Once the Mosquito slips into the same air block behind the contact, the instruments can only keep it in trail. Identification has to be made by eye, deep inside the bomber's defensive envelope, reading shape and external stores. The pilot advances the throttles, methodically reducing the separation distance. The gap steadily closes from 2 miles down to a close proximity. The interceptor must perfectly match the speed and heading of the heavy bomber to maintain continuous visual contact. The pilot must avoid any sudden movements that might trigger a defensive reaction or cause an accidental overshoot in the dark. At a calculated distance of about 600 feet, the undefined dark mass against the sky finally resolves into a distinct mechanical structure. The long fuselage and the massive wingspan become clearly visible. Crucially, the bulky, asymmetrical outlines of the remote-operated glide bombs suspended beneath the wings provide the final required data point. The hostile designation is confirmed. The visual gate is fully satisfied. The target is now verified physically rather than just electronically. With identification complete, the pilot fires a deliberate, aimed burst. At 600 feet, there is no margin. Return fire, debris, or a split-second overshoot becomes immediately lethal. The resulting exchange of fire critically damages the interceptor, forcing an immediate abort of the pursuit and a rapid emergency descent. The damaged Mosquito eventually executes a wheels-up crash landing directly on a secured beachhead. This emergency arrival results in a fatal ground collision with a transport truck operating in the landing zone. Now the question is, what failed inside the bomber when the rounds found the right spot? What mechanical vulnerability turned a localized cannon strike into an unrecoverable dive? At close range, the Mosquito's cannon finally connect. The rounds strike into the starboard nacelle and the wing root area. Fire takes hold on the right side. On this bomber, a local hit can turn into a runaway event because the right power system is a coupled installation. 2 DB605 engines are paired inside one nacelle as a DB610 driving a single propeller. The tight packaging reduces drag, but it also reduces fire separation. Once the nacelle and wing root are burning, heat and flame can spread through the coupled installation and into wing root systems fast enough to strip thrust and control on the right side. From roughly 6,000 feet, the aircraft drops out of stable flight and steepens into an unrecoverable dive, still burning, until it drives into the ground near Bolbec. The impact dynamics are governed entirely by this extreme terminal velocity and the steep downward trajectory. The aircraft strikes the ground with immense kinetic force, triggering a violent explosion that instantly fragments the primary airframe. This highly destructive event establishes a high-energy impact crater geometry. When an aircraft of this mass strikes the Earth in a vertical attitude, for the varying densities of its internal materials dictate their exact final resting positions. The immediate post-crash fire burns with intense, localized heat, fed continuously by the remaining aviation fuel. This prolonged thermal event fully consumes the lighter structural materials. The thin exterior aluminum skin, the internal fuselage framework, and the control surfaces are largely consumed, fragmented, and buried by the impact and the intense post-crash fire. The visible structure of the aircraft is effectively erased from the surface layer. However, the extreme density components decelerate differently. The 4 individual DB605 engine blocks and the massive steel undercarriage assemblies survive the explosion and surface fire, driven down by the steep dive like kinetic penetrators. They punch into the soft earth at the center of the impact zone, and bury in a near vertical orientation until soil friction arrests them 5 to 7 feet below the surface, about 1.5 to 2 meters. What remains above is only scattered incinerated debris. Below is a tight vertical column of iron and steel that defines the archaeological boundary and locks the aircraft's mechanical truth beneath dense agricultural earth. How could investigators locate this exact vertical column of heavy steel after nearly 7 decades of agricultural overprinting? By 2012, 68 years of plowing and planting have scrubbed the field clean. No crater, no scorch, no surface scatter. With the wreck buried deep, investigators have to connect archival clues to a target that cannot be found by sight or by shallow sweeping. In archival work and local correlation, led by historian Laurent Viton, can narrow the crash to the right sector, but not to an exact dig point. In working farmland, you cannot trench on an approximation, so the search has to be precise and non-destructive. Surface metal detectors do not reliably reach a deep, compact mass, and the plow zone is noisy with stray metal. So the team turns to geophysics, running magnetometer sweeps, and, where useful, low-frequency ground-penetrating radar to pick out a tight column of buried iron and steel. Sensor operators walk a disciplined grid across the suspected impact zone, ignoring scattered aluminum skin and wiring and watching live data for a distinct, sharp magnetic spike. Hundreds of pounds of ferrous mass compacted into a tight underground footprint. The sweep isolates one decisive hit. The anomaly stays tight instead of smearing into a broad trail. That profile matches a dense, localized mass buried several feet down, exactly what heavy engines and landing gear look like when they have punched in vertically. The search collapses from a wide field problem to one marked point. With the target verified electronically, the team establishes a physical perimeter on the surface. This electronic pinpointing completely alters the scale of the required excavation. By knowing the exact horizontal boundaries of the buried mass down to the inch, the team avoids a sprawling, earth-moving project. The boundary is drawn tightly around the primary sensor hit, restricting the planned ground disturbance to a small, surgically defined footprint. The surrounding farmland is entirely protected from unnecessary disruption. The wreck now has a precise surface coordinate and a tight excavation footprint. With the dense target isolated, what handling geometry was required to extract the masses from the deep mud? With the target packed into a deep, near-vertical column, the excavation has to open straight down. Dragging sideways would undercut the walls and risk a trench collapse. The plan is to expose each mass and lift it vertically once rigging is in place. Mechanical excavators then open the ground directly above the confirmed hit. The mechanical digging process is highly controlled. Operators remove the soil layer by layer, watching closely for the first signs of the dense target mass. As the bucket breaches a depth of 5 to 6.5 feet, the thick, wet mud finally yields to the primary structural components. The team visually confirms the presence of the 4 individual DB605 engine blocks. Alongside the engines, they uncover 2 massive main undercarriage legs, still deeply embedded in the earth. The site transitions from a mapped grid into a physical extraction zone. Exposing the heavy metal is only the first phase of the removal process. The immediate mechanical constraint is mud suction. Over decades, ground settlement has created a severe vacuum effect around the irregular shapes of the steel components. The wet clay firmly grips the engine blocks. If an operator attempts to hoist the mass directly without breaking the suction, the mechanical resistance will multiply the actual weight of the load. This dynamic force could exceed the safe working limit of the heavy lift straps, causing the rigging to snap under tension. To safely break the grip of the earth, the recovery team must enter the confined pit and manually clear the heavy soil from around the lower sections of the engines. This manual clearing allows air to enter the cavity, breaking the vacuum seal against the metal surfaces. Working in the deep mud presents significant physical hazards. The crew must navigate sharp, jagged edges of torn metal and avoid entanglement with crushed structural pipes. They carefully thread heavy-duty lifting straps underneath the engine blocks, searching for structurally sound load-bearing points that will not fracture when upward force is applied. Rigging the load requires precise handling geometry. The lifting straps must be positioned to secure the exact center of gravity for each irregular mass. If the straps are rigged asymmetrically, the heavy block will shift uncontrollably once it clears the trench walls, posing an immediate handling hazard to the ground crew. The straps are connected to the boom of the mechanical excavator, converting the digging machine into a high-capacity crane. The operator relies entirely on direct hand signals from the crew inside the pit to initiate a slow, highly controlled vertical hoist. The first engine block shifts against the remaining earth, fighting the heavy mud before slowly rising from the crater floor. The precise rigging holds the load steady, as the massive steel component completely clears the edge of the pit. Trapped water and liquid clay drain off the internal metal framework. The machine operator smoothly swings the boom, carefully lowering the engine onto the adjacent solid ground. This exact hoisting sequence is systematically repeated for each heavy target. Operating carefully, the team successfully lifts all 4 engine blocks and both main undercarriage legs completely out of the excavation zone. The primary mechanical masses are now secured on the surface. The extreme density of these parts allowed them to survive the initial impact and the long burial. However, resolving the core historical record of this aircraft requires more than just recovering its propulsion system. The team must look beyond the generic heavy steel to locate the smaller items that define this specific combat flight. Beyond the heavy engines, what specific recovered components confirm the bomber's specialized offensive and defensive roles? Recovering the engines anchors the aircraft type, but it does not prove the exact configuration of that night's mission. To match the record, investigators need diagnostic pieces that do not belong to standard structure, so the operation pivots from heavy lifting to careful, part-by-part forensic sorting in the mud. The excavated soil contains hundreds of distorted metal fragments, heavily encrusted in wet clay. The thick mud clings rigidly to every surface, completely masking the shape and identity of the individual parts. The recovery team must systematically sift through this displaced material, carefully brushing the dirt away from each anomaly before it can be categorized. They are specifically hunting for hardware that deviates from standard flight control systems or engine mounts. During this deliberate process, they uncover a heavily constructed mechanical subassembly, physically distinct from the previously extracted power plants. The complex gearing and thick metal plating differentiate it immediately from standard airframe debris. The investigators successfully identify this component as a remote-operated armored gun turret. The isolation of this specific defensive artifact provides a direct physical link to the documented combat exchange. The historical record states this heavy bomber utilized advanced defensive armament to effectively disable its pursuer before its own descent. Standard bombers of this era typically relied on large, manually operated defensive glass enclosures, which were completely obliterated by the initial ground impact and subsequent intense fire. In contrast, this heavily armored, remotely controlled mechanism possessed the necessary density and structural reinforcement to survive the kinetic destruction and burial. Its recovery directly corroborates the distinct defensive capability recorded in the historical logs. With the defensive perimeter of the aircraft verified physically, the investigation targets the offensive payload. The operational ledger designates this specific flight as a specialized strike against Allied shipping. To fulfill this distinct operational role, the aircraft was configured to carry HS-293 remote-operated glide bombs. Because the intense thermal event consumed the vast majority of the thin aluminum airframe, recovering an intact munition is physically impossible. The forensic proof threshold relies entirely on identifying isolated, high-density fragments of the weapon system that managed to survive the extreme temperatures. The sorting process focuses on aerodynamic shapes that do not conform to the main aircraft blueprints. Amidst the dense clay, the team recovers a highly distinct section of metal. The structural geometry, the rivet pattern, and the specific material thickness do not match any known control surface or horizontal stabilizer of the primary bomber airframe. Analysts inspect the artifact and identify this unique, specialized fragment as a suspected tail fin section belonging to an HS-293 munition. While the explosive warhead and the main structural body of the weapon were entirely destroyed by the kinetic ground impact, this single surviving aerodynamic fin acts as a critical forensic anchor. It provides the necessary physical validation of the specialized payload parameters listed in the archival mission documentation. The presence of this fin confirms that the aircraft was actively configured for its primary anti-shipping objective at the moment of its structural failure. These separated diagnostic elements elevate the recovery from a simple engine extraction to a fully validated historical operation. The remote turret and the distinct aerodynamic fin establish the undeniable offensive and defensive posture of the aircraft. They serve as the primary anchor proof for the entire archaeological effort. However, pulling these critical artifacts from the stabilizing environment of the wet earth immediately introduces a severe environmental hazard. The protective, oxygen-depleted seal of the deep mud is permanently broken. The raw steel, iron, and mixed alloys are now completely vulnerable to the open atmosphere. Once exposed to oxygen, how quickly would these raw components degrade without chemical intervention? Once the mud seal is broken, the clock starts. After decades in low oxygen, waterlogged clay, exposure to air, and shifting humidity can accelerate corrosion, especially on heat-stressed steel. Stabilization, controlled drying, and protected storage become urgent if fine markings and fragile surfaces are to survive. This rapid degradation threat is a direct consequence of the fire and mud artifact degradation cycle. The initial intense post-crash fire altered the metallurgical properties of the surviving engine blocks and heavy armor plating. While the extreme heat completely consumed the thin aluminum airframe, it heavily baked the dense steel components, creating porous surfaces highly susceptible to moisture absorption. The deep mud then bonded completely with this heat-stressed metal over the following decades. To halt the structural decay, the conservation team must safely separate the hardened clay from the damaged steel without inflicting further mechanical harm on the fragile underlying surfaces. The stabilization procedure requires extensive and highly controlled cleaning protocols. The artifacts are transported to a dedicated conservation facility where the thick, caked earth is carefully washed away. This process must strictly avoid high-pressure abrasion. Applying aggressive mechanical force to speed up the cleaning would easily strip away delicate surviving manufacturer plates, faint original paint traces, and the exact physical damage signatures resulting from the intense heat and ground impact. The team relies entirely on low-pressure water baths and deliberate manual brushing to gradually expose the raw metal surfaces underneath the agricultural soil. Once the heavy engines and the defensive turret are completely cleared of soil and thoroughly dried, the chemical stabilization phase begins. Leaving the heat-affected steel exposed to typical ambient humidity guarantees a continuous cycle of rust accumulation and eventual structural failure. To permanently prevent this outcome, the conservators apply specialized industrial corrosion inhibitors across all exposed surfaces. These specific chemical agents are designed to penetrate the microscopic pores of the heat-stressed metal. The treatment systematically displaces any trapped moisture within the iron structures and forms a durable, microscopic protective barrier against atmospheric oxygen. This thorough chemical application effectively freezes the physical condition of the recovered components, locking the historical damage in place and permanently halting any further material loss. With cleaning and chemical stabilization complete, the recovery reaches its endpoint. 3 treated engine blocks, along with a remote-operated armored gun turret and the suspected HS-293 fin, are preserved for permanent display at the Wings Aviation Museum in the United Kingdom. A 4th stabilized engine is retained in France for public exhibition. What remains is not a rebuilt airframe, but surviving evidence. Components that pin the story to a place, a date, and a failure chain.